Hi everyone, this is Veer from the Math of Student Competition team, and welcome you all to the second session of the Vehicle Design Webinar Series for Student Competitions. So today we'll be talking about vehicle powertrain modeling. We'll touch base on that, and then we have Krishna Teja from JK Tires. So he'll be talking about full vehicle simulation, and he has a lot of content to share with you. So you have to bear with me for some time. And along with me, I have Sudhakar, Pratyay, and Himanshu who will be supporting the event. Now, just a few recap thing for the webinar. So this is the series which we are doing this October and the month of November. So first one we conducted on vehicle dynamics, focusing on vehicle dynamic simulation. So if you have not attended it, you won't be getting the links for the recordings. However, we'll be publishing the recordings. So if you haven't, you can reach out to us at racinglaunch@mathworks.com with the email saying that you want the recording, or you can also join our Facebook group, the link to which we'll be sharing at the end. Then today we have this completely dedicated session on vehicle powertrain modeling and full vehicle simulation. And then on 11th of November, where my colleague Sam will be presenting, so it will be beyond simulation. You will touch base on how to communicate with CAN networks using vehicle network toolbox. So if you haven't, again, we have shared the link in the chat. You can register for the 11th November session as well, where you will be learning communicating with CAN network using vehicle network toolbox. Now, there are a few quick important things before we deep dive into the webinar. Uh, if you have any technical questions, please use the Q&A section and make sure that you're sending to all the panelists. And then chat box will try to use it for interacting with each other. So we'll be asking some questions, only a few, not a lot of questions. So you can answer that in the chat box. And then if you have some non-technical things, for example, that can you zoom in, zoom out, it's not audible, the video is not proper, that you can mention that in the chat box. Certain questions coming up that you're not getting the email. So we haven't sent the email yet for the last session. We are in the process to publish the recorded video for the last session. We'll send you within 5 to 6 business days. So you'll be getting that. Otherwise, if you're not getting that, as mentioned, you can reach out to us at racinglaunch@mathworks.com. Again, we'll share the contact details and the link to the Facebook group at the end of the session. Okay. So in the last session, we covered this. We covered these topics: racing line optimization, uh, where we saw one of the submission from Jacob submitted his project for the MathWorks Excellence and Innovation Program. And this was also an introduction to MATLAB. And we also shared a lot of resources from where you can download the code. Then Sudhakar, my colleague, he spoke about equation-based vehicle modeling using Simulink, where he demonstrated how equations can be converted into a block diagram representation. Further, we used vehicle dynamics block set to model longitudinal and lateral vehicle dynamics, and we also saw how you can add one driver, which was a Stanley driver, to track certain path. And then finally, we also covered in detail the multi-body suspension system, which is a part of the SimSkip vehicle template. And we also demonstrated that from 2021B, you can also add a tire model to your multi-body vehicle model. So this all, again, if you have missed it, don't worry. We'll be sending out the resources, and you can reach out to us on racinglaunch@mathworks.com for more. So with this, we'll have some exciting agenda and a little bit tight agenda today. So we'll be focusing on physical system, modeling of physical system. The whole session, I would say 1.5 hour session, will be approximately, I think 50 minutes will be dedicated towards modeling of physical systems, wherein we'll see a very basic battery electric model with motor cooling, which will be based on the fundamental blocks. And then we'll little bit improve, or you can say add more details to a model where we'll be seeing how electric vehicle can be powered by BLDC motor. And then in powertrain block set, that is also one of the toolbox what we have. We have multiple vehicle reference applications which you can use for your different design purpose. So that also, in that we'll check out one electric vehicle reference application. And then we'll see that how Simscape, which is you can say equation-based modeling, and Powertrain blocks of which is a data-driven modeling, how you can integrate these two. And then Krishna will come with his full vehicle simulation, and he has a lot to speak and lot to show, and also he has a very nice introduction of himself. And then we'll share some resources, and then we can take some questions. So with this, uh, as we mentioned that most of the part we will be focusing on modeling physical systems. So let's bring one image in front of you, and a very easy question for all of you. Uh, what is this like from the image, from the physical system layout, what you see? What can you think of this? What is this? You can write your answer in the chat box. You have 1 minute. Thevenin model, okay. RC circuit, okay. Equivalent circuit, RC circuit. Yeah, that's correct actually in electrical terms. But in terms of application wise, what do you think? Like, which part it is for an electric vehicle? Battery modeling, okay, okay, okay. Single cell model, yeah. And that's yeah, that's a correct answer, I would say. Yeah. Okay, Krishna is also answering. Thanks, Krishna. Yeah. So this is a battery or single cell model. Now, the idea behind just to putting a rough diagram of this RC equivalent circuit or battery model, one cell model, is that this is what the physical system looks like, or physical system layout when we say. Similarly, you can also make one layout for a DC motor. Okay. So this is, as you all said, battery equivalent circuit. And to model this physical system layout or physical systems, we have a very, interesting and exciting, amazing tool called Simscape, which enables you to model physical systems. And what are these physical systems? Systems like thermal system, electrical system, mechanical systems, something that you can see, you can feel, you can touch, and define by using laws of physics. And the one important thing is that, uh, you must be seeing a lot of text on the slide, but the most important thing is basically it is just mimicking the physical system layout on a simulation platform, which is Simscape. So consider a DC motor. Now, if you have to make a physical system layout of this, it will be having certain physical components. What are those components? Those components are resistors, inductors, electromechanical converters, and then for the load, you'll be having certain inertias. So now, when you're modeling that in Simscape, so Simscape provides a certain good amount of physical blocks, wherein already the equations have been written, and then these each connections, like for example, over here, if you see these resistors, inductors, electromechanical converters, inertia, these are already having a set of equations, and these are interacted by energy exchange. So even the signal, the physical signal, what you see, it is having certain meaning over here. So as said, it is just a replica or mimicking the physical system layout on a simulation platform. As an example, here is a DC motor where you can see these elements. These elements are already having the equations. You don't have to derive it from scratch. You can connect it the way you connect in a real environment. And what you can further do is like, for example, we are giving you a lot of different physical blocks which are there in Simscape library. And if you want to customize it, for that, you can use Simscape language. For example, over here, you can see that we wanted a lossy ultracapacitor, a custom made block. So for that, you can use Simscape language. And then what you can do, so here's a long list, but in simple words, since this is a webinar dedicated for powertrain modeling and basically full vehicle simulation, you can make an electric vehicle model, and you can perform optimization. You can do component sizing and selection, and this is all code generatable if you're connecting it to the hardware or sending, if you want the code to be run on a hardware. So important points from this is it is mimicking the physical system layout in a simulation platform, which is Simscape, and then there's an energy transfer involved between these two components. Now, once we say energy, this energy flow in this physical system, that is dependent upon across and the through variable. Now, why we are telling this? Because this is helpful when you are making the connection, because it might happen that if you want to sense something like torque, or maybe you want to sense angular velocity, in that case, how to do the connections? So across variables if you want to sense that, that is connected in parallel, and through, that is connected in series. So here's one example in electrical terms. So power in electrical terms can be defined as voltage into current, where voltage is across and current is a through variable. So when you want to measure or sense voltage, so that has to be connected in parallel. And if you have to measure current, that has to be connected in series. Similarly, in mechanical terms, this power can be defined as angular velocity and torque. And now, if you're making the connection, this is how it will look like. So in the first top diagram, you can see that we want to sense the angular velocity. So these are connected in parallel. And then we want to sense the torque. For that, we are putting the sensor in series. So these are certain basic things. And I mean, a lot of other things are also there. Eventually, when we move through step-by-step different models, you'll get an idea, and we'll also share you some resources. So, but you must be wondering that how do I remember all these? Like how, which variable is across, which variable is through. So for that, no need to remember. You can just follow the sheet. This is also in the documentation. We'll be sharing that link as well. And even when we start the modeling, we, at least if we have any confusion, for example, isothermal liquid, you can see that across variable is absolute pressure, and then through variable is a mass flow rate. So you can just follow this and you can build your own model. Now, what we'll do next is we started with this equivalent circuit model. So we are not going deep dive into battery modeling, but we'll just, with this motivation or with this problem statement or this physical system layout, we'll see that how connections are made and how easy it is to make the connections, and like few important things what we have covered. Once we are done with this, then we'll move to a live demo of electric vehicle, basic electrical model with motor cooling using fundamental blocks. So let's switch to MATLAB. So let me go through this first, the library browser where you can find these blocks. So once you open the library browser, you can see over here that so you scroll down. Here you can find Simscape, and in Simscape you have driveline, you have electrical fluids fundamental library, and multibody. And so we, in the last session, we spoke about multibody, and a few also we touched base on driveline. So since we are looking into an RC equivalent circuit or a battery equivalent circuit, so let's get into the fundamental library and see where you can find all those physical blocks or elements. So in the electrical, when you go inside electrical elements, you can see over here that you have these electrical elements: capacitor, you have resistor, you have inductor, which are all needed for when you're going for this kind of circuits. So now let me do one thing. I'll just like add the image in this blank canvas. So if I go to this and so this is just a way to easily build any model. For example, if you are planning to make any model, for example, this battery or DC motor modeling. So in that case, this is how the first step should be. Like if you have a layout of the system or a equivalent circuit, whether it is electrical or even in mechanical, you can take example of spring mass damper system. So just keep an image, and you can have this in the library on one side, and you can just keep on just adding the different elements of physical blocks over here. So for example, like I just dragged in this capacitor, and when you double click on this, you don't have to define any equation over here. Over here, what you need to do is that you need to define the capacitance and different variables. And one more important thing is that whether you use any mathematical modeling or a physical modeling approach, the important thing is that to get the realistic results, how you define the parameters is really important. So we have seen students working on this physical modeling. They have a nice, model with all the proper connections. But if you don't feed the correct parameters, then it's hard to, get proper results. And it just makes sense also for any kind of modeling method. So we'll bring in capacitor. Similarly, we'll bring resistor, and you can see we'll just make, similar connections over here. So like this, and we'll just bring one voltage source, and we'll just simply connect it. So you can see that we're just mimicking or replicating the physical system layout over here. And then you need to just connect to the load. We'll see like how we are connecting to different loads and full vehicle. So this is just, say just an example of how easy it is to just mimic the physical system layout over here. Yeah. So again, what we'll do is, we'll take this as a motivation, and when we are moving to a electric vehicle model, we'll show you that how just with this equivalent circuit approach, we have built a whole battery pack, and then how we are simulating it to a vehicle dynamics model. Okay, so this is just a starting. Okay. Now, I know that a lot of you are interested or looking forward to learning battery modeling. So fortunately, we have a good amount of resource, and the best resource for you all is this page. You can visit this page, battery modeling, and you can get here good amount of information like battery modeling, finding the state of charge, state of health, and different, and even battery management system. So you have videos, tutorials, documentation, and doc examples. You can have a look into that. Okay. Now, moving to our main goal, that is modeling an electric vehicle model. So we'll start with a very basic fundamental model using fundamental libraries. Like for example, when I'm talking about the fundamental blocks, so basically these are all the blocks which are coming from here, the fundamental library. So now let's move ahead and see what's the problem statement. So consider this vehicle, and this vehicle is comprising of battery, it is having a motor, then it is having a gearbox, and then it is driving the wheel, and when it is driving, it is having the aerodynamics effect. Now, if you have this model, what all you can do? First thing, you can size the components, you can estimate the battery performance, you can study the vehicle performance, or you can also design a motor cooling system. So we'll be taking this as an example, and the scenario is something like this, where the vehicle aim is to overtake this, and from here we'll derive or you will size the motor based on this scenario. And further, we'll also look into like how you can build a basic, very simple cooling system for the motor. And so what you need to do is, like for example, if you're starting with the Simscape, either you can just start with a blank canvas, or you can just type ssc_new and open one canvas with some important default blocks which will be by default needed when you're modeling it. Okay, so we'll come back to what all these are. So you just saw the vehicle was having one wheel, it was rotating, then it was having some aerodynamic effect, and it was also having gearbox. So what we'll do is we'll try to make this with a very simple approach. So first thing what we need to do is we need to rotate that wheel, right? So for that, we'll just bring one idle torque sensor, torque source, okay, where C and R are the mechanical conserving ports. And then we have a tire, a simple tire, okay, where again AH and H are mechanical conserving ports. Now to vary the torque, what we'll do is we'll add one gearbox. So we'll add this to one port to the ideal torque source, and then this will be connected. The other port of the gear will be connected to the tire. Now, to define the inertia, to include the inertia, we'll just bring one mass. We'll make this 2-port because you have to make some other connections as well. We'll just rotate it and make the connection. So, I mean, as we are building it, you can see that we're just replicating the physical world. We want to rotate the gearbox, and then we want, I mean, through which it will rotate the tire, and then we want to include a mass, which is a vehicle. So, few things. We'll just attach this to a rotational mechanical reference, and then we have to add one constant over here. I mean, just adding some kind of some constant torque, not the signal, but it's constant. So now if you see over here, there's a change. What is a change? That if I type constant, by default gives you one Simulink block. However, as we already mentioned that these are all built using physical signals. So that's why this is a PS constant, physical signal constant, which is connected to this idle torque source. Okay. Now further, what we want to measure the velocity of the vehicle. So for that, we just bring one idle. Okay. So we bring this idle translation motion sensor. Why? Because we want to measure the velocity. And then we again do the same thing. We connect the conserving ports. And further, there's one more important thing which is lying over here, that is the solver configuration. So as already mentioned, that these are all physical signals. So for this, we have to add this solver configuration block in all of the physical networks. So what it will do is it'll make sure that it is solving this physical signal, and then overall, the model will be solved using the global solver in Simulink, what is present over there. So further, there are a little bit more connections over here, which will make it. And then, so we covered, I mean, how the connections are made. We covered why the solver configuration is present over here. And then another aspect over here is that already mentioned that these are all physical signals. So for that, if you want to visualize it with respect to time, you need to connect it to the scope. So for that, we need to convert the physical signal into Simulink. So this is how the architecture looks like. Now, what we'll do is we already have the model with all the parameters, because if I again start adding the parameters, it will take a good amount of time. So I'll just close this one, and we will move back to the model which is already there. Okay. So now over here, you can see the same thing. We have this torque source, you have this gearbox, tires, chassis, and everything. Now let's run this model. So if you run this, okay, yeah. So if you run this, you can see that the velocity is continuously increasing. And one more thing, what I mean, I forgot to mention is that when you're connecting these Simulink block to SimScape using this converters, so here you need to define these output signal units. So for example, this we have defined kilometers per hour. And you can see that this is way too fast. I mean, you won't be able to drive with this velocity. So now what is missing? We are missing with rolling resistance. We are missing the inclination effect in the vehicle, and even the drag. So what we need to do is, again, over here, we'll add some more blocks, 2 blocks to include that resistance. So going to that model. So now with that improvement, what we did is that we have added a block called translation friction, which is accounting for the drag. And then for the inclination, we have added one idle force source to which we are giving some constant value. Okay. Now let's see what happens. Okay, one second. Okay. So now you can see that, okay, the effect is much better. It is after 400 seconds, you can see that velocity, I mean, the vehicle is approaching the constant velocity. What do you think? Like, is it fine, or we need to make some changes? You can type that in the chat box. So given it, I mean, if you want, if you're looking from, I mean, the send in the model and even the results what you're getting, what do you think? Like, what could be wrong in this model, or is everything fine? Gear shift effect. Okay, Aditya says gear shift effect. Okay, so what is the effect of suspension? Yeah, I mean, uh, coming back to the suspension, yeah, we have not added suspension, but still, like at your basic modeling, you can add few more things, or like the major concern over here is that this part. This, you can see that the vehicle is moving very fast. So what we'll do is, if you remember the scenario which we are talking about, we are talking about the scenario where the vehicle has to overtake the other vehicle in one lane and come back to its original lane. Okay. So what we'll do is, here we'll try to control the speed. Okay. So for that, we'll add one driver, the driver which is dedicated for those, I mean, that kind of overtaking. So going to that model, to the driver, over here, if you see now, uh, just so that you don't confuse, this driver model is not a part of like any toolbox, or not a part of any Simscape block. It is just created using Simulink blocks. So if you go inside this, okay, and the task is to controlling the velocity. Now this driver model is having currently, you can say that 200 Newton meter torque. Now let me run this first. And now you can see that, okay, this is, to some extent, it is fine. I mean, it is having 100 kilometers per hour over here, and then it is increasing the velocity when it is overtaking it, and then it is coming back to constant. Okay. Now, coming back to the component sizing and selection, which still is a question, is that if you want to, I mean, select a proper component or motor for this. So for that, you have to get into or visualize a torque. What is the torque output? So for that, you can use the Simscape result explorer, where you can explore the results from different Simscape blocks with respect to time. So if I go to gearbox, and if I see over here, and let's expand it. Okay, I closed that window. What? Okay, let me again start that. So over here, you can see that it is taking like around close to 15 seconds or 14 seconds to overtake, which is a like good amount of time. Now to this, so first problem was controlling the velocity, which we did just adding one driver. And then if you want to reduce the time to overtake that vehicle, so let's do one thing, let's increase this torque. So if I increase this torque and further run the model, and then again visualize the results, let's see what happens. So now you can see over here that this is much better. Now it is taking around uh, less than, I mean, less than 4 seconds, which is perfectly fine. Now the whole conclusion of the story is that, I mean, when you have certain targets to achieve, based on that, you can build the model, and then you can size the components. So from here, we can at least say, there could be a lot of other parameters, like I'm seeing the uh, this chat. There's drag people are telling, then lateral dynamics they are telling. There are a lot going on. But the overall thing is like, this is how the procedure is like when you're looking for component sizing and selection. Now with this, we understand that if we have this, if you're selecting some motor, which is having maximum torque of 800 Newton meter, that motor we have to select. So that's what we did. What we did is in the next model, we have added one motor. So wherein you need to define certain parameters. This motor is designed based on velocity and torque. And then you have to define these certain parameters. And once you have defined it, and then when you run it, you can see that it is within the range and it is below 5 seconds, and it is fulfilling all the requirement. So we saw that we started with a very simple basic model. It is still a simple basic model, and how we decided on what kind of what should be the specs for the motor selection. Yeah. So this is one part of the model. Now the another, okay, there are a lot of questions. Okay, one I can take. Why connect driver between scope and PS converter? Okay, why connect driver between scope and PS converter? Yeah. So the thing is, so this question is asked, I think 2 times, why connect driver between scope and PS converter? The reason is that this is completely built in Simulink. So that's why what we are doing is we want to input the Simulink signal, which can be done using this converter. And again, we want to give back the motor over here. What you see, this requires the torque as a physical signal. So that's why we are using another converter over here from Simulink to physical signal converter. That's why we are connecting it. Yeah. So like you can definitely keep on asking the questions. Once we are done with the session, we can come back and go through it. So having said that, we just saw the model, and now another task which we already spoke about was that how to uh, how to add the thermal effect, or how to design a cooling system. Now, now at least even if you're new, you got an idea that it's just that what you see in physical environment or real environment, that's what we are trying to replicate over here. So with that learning, what do you think that, and one more hint I'm giving over here, that this H port, what you see on this is the thermal port over here. So when you double click on this, you need to define certain like thermal mass and initial temperature. So now suppose we want to add one cooling system. So what do you think, like what are the components would you need? Or maybe before that, what kind of different heat transfer will take place from the motor to the environment? What are the different modes of heat transfer which will take place? If you have that answer, I think it's very easy to understand, like when you're modeling the physical systems. Okay, Mayur says convection. Okay. Okay. So there's one interesting answer: conduction and convection. Conduction. Okay, yeah, conduction and convection. Nice. Fine. Just on a simpler note, yeah, I think most of you are correct. Of course, convection will be there because it has to dissipate the heat into the environment. So it's through fluid state, it will be convection. So that's one. And then conduction will be also there because motor will be in certain casing. Okay, so for that, it is a heat transfer through solid medium, so it will be conduction. So it will be having, so now when you're modeling it, when you're adding that thermal effect, it will be having conduction as well as convection. So with that, we'll go to the final model, how it looks like. So currently just follow, focus on this one. Let me zoom it a bit. Yeah. So what we did, so as you all answered that conduction, yeah, this is with the casing, heat transfer through solid medium, and then to the environment, that is heat convection. That's why we have put it over here. And then we have certain temperature sensors and other source blocks. Now further to cool it, so the cooling, how you can do the cooling, you can have, I mean, here we're talking about the liquid cooling. So that's why what we have done is that we have added two pipes. Okay, this is a pipe casing which is connected to the casing over here, which will through which I mean the fluid will be going, and then to dissipate that heat, we are connecting that to the ambient or the ambient temperature, or you can say the atmosphere. And then there are certain blocks for, I mean, which for which you have tank, pump, and then to define the fluid properties, we have one more physical block. Now, once you run the simulation, what you see over here, Ahmed, can you send the model? Yes, we'll send the model. We'll show you something interesting, where you can find the model. Now, what we did is I just switched off the cooling system, and now let's check out the temperature, what's happening. So if you have some threshold value, something like 120, you can see that it is crossing and the temperature of this motor is increasing as the time is increasing. Now, when you add this cooling system, let's see what happens. So, so yeah, there's one question meanwhile I can answer is what Simscape libraries are needed for the model with cooling. So yeah, I mean, along with what you saw, we took some models, made some blocks using fundamental libraries, but otherwise you need to go into the fluids and you can check out these blocks, which you can find these pipes and all. So yeah, I mean, now I switched on that cooling and you can visualize over here that this is within, okay, no, not this. So now you can see that this is below the threshold point and we are able to cool the motor. So this is just, I mean, I would say very on a basic level, we showed the model. And now what we'll do is we'll move into, I mean, more detailed electric vehicle model where you will see that how we are adding a specific motor and battery as well. Okay. I hope, I mean, you got some idea to, again, to download these models. This is the link. Okay, so this is basically what I spoke about. I mean, what I demonstrated. It is completely in the form of one of the videos, so that you can find. I mean, the models you can find over here. The battery electric vehicle with motor cooling in Simscape on the file exchange. It also, this is also connected to GitHub, and this is also, there's also a link to the video tutorial to this, so you can have the model from here, and you can also again watch the video to learn like the same messaging basically. Okay, so moving to the model, let me close a few one. Okay, so yeah, so we'll just quickly run over one more model which is having more detailing, because when you talk about the electric vehicle model, you have DC-DC converters, you have motors, specific motors. So now you can see over here that when we go to the vehicle block, we are not modeling it using mass and drag using a friction block. Rather, we have a dedicated vehicle body block, wherein you can, where if you double click on this, you can see that this block is incorporating the equations, which is having mass, then number of wheels per axle, and then CG height and everything. Now, it also takes into account the drag, pitch, and all. So this is one block, and then it has certain connections for making connections with the tire blocks, and then brake as well, and putting an inclination. Now, with this recent release, we have this interesting one more block in the driveline, which is called longitudinal vehicle, which is also incorporating the tire effect. So you don't need to, I mean, separately connect tires like what you saw in this model. Okay, so you can also have a look into this one. And further, if I go ahead, you can see gear systems, which are modeled using these friction clutches. And based on that, we have certain logics. And then as we mentioned, the battery pack. So if you go over here, you can see that how we have utilized equivalent circuit model to make one cell, and then we have connected that and to make a whole battery pack. Okay, just to confirm, is my screen visible to everyone? Uh, okay, so you can see the screen. Okay, fine. Okay, perfect. So, so we're talking about the battery model, how we utilize the single cell equivalent circuit into a whole battery pack. And then coming back to the motors, now we are not using the motor which is built on using torque and velocity values. Rather, we have a BLDC motor. Similarly, you can have PMSM motors also. You can check the Simscape library and you can see what are other motors we are having. And then we also have, we have also built one DC-DC buck converter to step down, and then three-phase inverter for this one. We're controlling the switching pattern using commutation logic. So again, you can see. So you can see, you can, as a learning perspective, you can start with a basic model, and then, I mean, as you proceed further and as you understand the concept of whole physical modeling in Simscape, then you can add more details into the model. Now, how this model can be used? For example, in Formula Student competition for component sizing and selection, if you are sizing your battery, if you're selecting your motors, I mean, you must be having some kind of drive cycle. You can have that drive cycle over here, add one controller, which could be simple PI controller, and then you can see that, okay, the powertrain which I designed, that is able to track that velocity or not. Similarly, you can also optimize it. For example, you can run certain optimization to find the parameters of this motor. So that's what I mean. We wanted to show over here that how you can increase the fidelity. And if you want more high fidelity models, what we would recommend is do check out this resource, which the Simscape vehicle template. We also spoke about this, and we also took one model from this and demonstrated you in the last session, the suspension model for the Formula Student teams. And you can get a lot of information from this, even because it includes one axle, two axle, multi-axle vehicle models, and with powertrain and vehicle dynamics as well. Okay, so you can explore this. We have provided the link over here, and yeah, feel free to, I mean, use these models for your specific requirements. Perfect. So quickly, what we will do is, we don't have much time, since we have to give it to Krishna, is until now, we just spoke about a concept of physical modeling. We also have one more tool called Powertrain blocks it with a goal to providing starting point for engineers to build good plant controller models and provide open and documented models. For example, this toolbox has a good amount of reference applications. You can use that reference applications by changing variables, or if you want to make any changes to any of the blocks, these all blocks are open. And of course, those who are interested in or looking for hill testing, so it provides very fast running models for that. Now, what is this Powertrain block set? It provides you different libraries for drivetrain, energy storage, propulsion, transmission, vehicle dynamics, and vehicle scenario builders. And you can combine these models to, for example, build one engine model, and then that subsystem can be added to a complete full vehicle simulation, and then you can visualize the results or do the analysis part. So these are the whole set of reference applications over here. And what we will, these full vehicle model, and we'll just check out one example for the electric vehicle one. And then we also, if you are looking for virtual engine dynamometer testing, you can also check out these reference applications. One is for CI engine and another one is for SI engine. So I'll quickly just open this model and show you that how you can leverage this model for your specific requirement. Yeah, so this is the model. What you see over here is it is having passenger car, it is having different subsystems. And if you go to the passenger car and you go to the electrical plant, you can see that how the powertrain has been built using blocks from powertrain blocks. For example, if I just take example of battery, so this is the block which is present in the powertrain block set. Again, over here, these parameters you need to define to model the battery. And just to again, remind you, these are not physical signals. These are based on Simulink. These are based on equations, and you can see that these are having directions. So you can say input signals and output signals. Now, if you want to change it, or you want to visualize it inside what it is, or you want to customize it based on the existing blocks, so you can simply go inside this, press Control U, and you can see that what are the equations being used over here. So it's completely open. You can use it, you can modify it, or you can use directly just use the reference application. Similarly, these are other with the other components as well. Okay. So now this model, if we run, it will take some time. And since we don't have much time, just quickly I'll mention that this is a closed loop model. What it is doing, it is having a reference drive cycle. Again, this is the FTP75 drive cycle. For this, we are running the model, and then you can see that how smoothly it is tracking, and then you can also calculate other parameters like state of charge for this electric vehicle model. And we often get a lot of questions regarding, can we have other drive cycles? So if you just click on this install additional drive cycle, it will route you to one of the support packages from or submission on the file exchange. From there, you can get more drive cycles for testing. So with this, we'll just give it to Krishna. Okay, so Krishna, I'll just make you as a presenter. Let me know if you are able to get that access.
Thanks, Veer, for the first of all inviting me for this webinar, and I hope it has been a great presentation already, and a lot of things and very detailed are already covered. So what I'll do is I'll first run you through a few slides which actually describe like how a full vehicle can be modeled. But before modeling that, I would like to give you a small use case that we have done. Of course, it's a very big project, but I'll try to compress it within 4 or 5 slides, and it'll basically to make you understand like how different parameters affect and how in real vehicles, how testing is being done on track. So with that small intro, let's get started. So basically, I have done my PhD at IIT Madras in terms of vehicle dynamics and reinforcement learning control under Professor Krishna Kumar. I think many of you might be knowing his NPTEL and YouTube lectures on vehicle dynamics and finite element analysis. So I've joined JKTIS recently and primarily focus on driver-vehicle interaction and basically using software in loop and driver in loop, hardware in loop simulators, tire tuning, and ADAS systems as well. So just to give you a feel, so this is a view of our lab, and at the bottom you can see me driving the hardware in loop, or basically you can call it driver in loop system as well. And the car that you see on behind is the same thing basically. So, but this requires extensive parameterization, extensive modeling, and all that stuff. And these are some of the things that we are going to explore in the forthcoming slides. In a few minutes, we're going to see that. So Veer has already given you a very good basic understanding of the difference between equation-based, that's on the left side, and physical model, that's in the center. But the physical modeling is basically, again, categorized as 1D and 2D, because in 1D, basically you do not have gravity or any other inertial effects and so on. So that is where we go into 3D to model even more details and combination with 1D simulations as well. So this is what we're going to explore more in detail. So the simulation model basically has all the subsystems that you see, that from the chassis, the suspension, tires, brakes, steering, maybe power steering as well. Today everything is electronic power steering. If you go to German vehicles, European vehicles, basically they do not have a mechanical steering as well. It is called steer by wire. So everything is replaced by wires. So how those can be modeled. And powertrain is already covered. So I just will go through the basics. And formula students might be interested in aerodynamics. So I'll just give you a brief of how do you model aerodynamics. extensive modelings can be done, but here I'm going to just touch the basics. So to give you a feel, I'll first run you through a case study. So the case study is regarding objective handling performance. So handling is basically extensively dependent on these subsystems: tires, suspension, and steering system, of course. Of course, vehicle level parameters and other parameters are not very well felt, but these are the main parameters. So for these performances, for example, a new tire is going into the market or a new vehicle is going into the market, it needs an extensive validation, not just on the sensor side, but also the physical feel of the driver. That is, what is the subjective rating needs, which the driver himself gives. So we require different metrics from individual components, we require overall metrics of the vehicle itself. And the challenges are pretty big. We need a full vehicle CAE simulation and overall process efficiency in data collection, modeling, simulation, testing, so on. The biggest challenge is which physics to model and which we can omit. So the trade-offs are huge. So these are the things that we need to address before. And once these are done, we can actually have a correspondence map, like which performance metrics is affected by which parameters. So that is what we are even going to see in the course of this presentation. So first, we are going to measure the tires. So on the left is what you see is called as traction trailer or skid trailer, basically, which measures all the tire forces and moments under different conditions. And from those raw data, this is a skid trailer that is available in India. It is the first that we have purchased and we use extensively for tire measurements. Next, we estimate all the tire data, again using MATLAB as extensive optimization and estimation techniques, codes built in, so we can directly leverage them. Finally, we perform the simulation, full CE simulations, as you can see on the slide. Next is vehicle parameter estimation. Of course, you can have data from KNC machines, or we have experimentation protocols. Some of them are published online. You can get these papers online. So once we model them and use a parametric estimation with sensors that are mounted, you can see here few sensors that are used for suspension, and for vehicle level testing we have RT3000 steering robot and so on, which to capture and maintain certain conditions of test protocols. On the right side you see the measured data and estimated data match that. The next important part is the steering estimation, which the models are quite obscured, and because it requires a lot of custom models to use them. I'll explore some of them during the course of presentation. How can you model such things in MATLAB easily? Again, without having to worry about a lot of equations. Simscape is there to alleviate from all of this stuff. So the blue one is on the road testing, and the red one is from the simulation models that we do. On the right side that you see is a steering robot, which gives specific inputs repeatably on a test track. So the mix of all these things, now we know the tire parameters, we know the vehicle parameters, we know the steering parameters. So it is like we are making a digital twin of the complete vehicle system. Only once if we have all these parameters, we can actually verify or validate vehicle level data. For example, here it is lateral acceleration versus the steering wheel angle. And it's with different tires, if tires change, the behavior also changes. On the right side is the same car you see behind. So you can sit inside and drive, the driver actually drives, and we can mount the same steering robot to repeat all the tests in the hardware in loop system. So we can have a very good correlation. So that being said, so let's, so here is the question for all of you. So this is one of on the LinkedIn posts. On the right side, you see a simulation that is running, actually it's from the test track. And left side, you have 4 graphs. So those who are into vehicle dynamics, they need to be on to the parameters or the data graphs. So few of them have identified the first graph as steering hand wheel versus steering torque, which actually gives you the feel of the driving that you drive on road. So can anyone guess what are the other graphs these are? And what is the legend? What is the difference between blue and red? Can anybody do that?
Krishna, you can see the chat, right? I mean, what they're writing as answers, right? Can you see?
Chat, I'm not able to visible for me.
Oh, okay, so okay, no issues. So I'll so I mean we got two answers.
Yeah,
I think
the screen has slipped up. Okay, fine.
you can see it, right? Okay, fine then. Okay,
Yeah. So on the right side, that is the second graph. What you see is the steering handwheel versus lateral acceleration. So there are a few thumb rules. If you are into racing team, you might be knowing many of those things. So a few thumb rules is that at a certain speed, if you give certain steering angle, it should reach certain lateral accelerations. So most passenger cars, the thumb rule is at 60 kmph, near 60 degrees, you need to be able to reach about 4G. 4 meter per second square, 0.4 G. So these are few thumb rules, and this is yaw rate, which actually tells you are you heading in the proper direction, or you need to basically it tells your vehicle is understeer or oversteer characteristics. And this is the roll angle, which actually gives the driver perspective. Is it driving the vehicle safe, or the roll is causing him anxiety? There's a lot of stuff that is going on around the roll and the perception of yaw rate what the driver feels, maybe using the ECG and EEG signals and so on. So that is some of the active research that we are doing at our lab here. Yeah, so that's great. And the legend is the tires. So the blue the blue color that you see is, of course, for a very close cousin of for this vehicle. But the red tire you see, because it has some kind of issues, it is for a smaller segment of tire. Basically, it's for a hatchback, and the blue is basically for an SUV. So SUV is bigger car, and that's its performance is good, but it reaches nearly 4 meter per second square. And the smaller tire, it is made for a smaller vehicle, so it does not reach its full capacity, or the vehicle does not behave as what you expect when you drive it. So the parameters are literally important when you make a simulation. So that said, let's continue further. So these are the subsystems that we have seen before. And since I've brought up a use case with respect to handling, I'll give more focus to tires and steering and suspension. Brakes in terms of ABS, I'm going to go into more detail, and others I'll just touch up a bit. So you have a complete picture of how the full vehicle is being. So let's start into one by one. So the body is basically to attach different axles to the vehicle, center of pressure for aerodynamics to give additional forces or moments if you have such kind of things, or even to connect additional bodies. For example, trailer. In such case, trailer we are going to see in the coming slides. But if you have all the stuff, you can add them. And if you see here, and you see an additional external torque and forces block. So this is where you give the aerodynamic forces near the CG, of course, basically an offset of CG to center of pressure, and that is where you act. And from the CG, I have front and rear axles, their positions, and a CAD basically to maybe for beautification or even the inertial properties and so on. And the base port is connected to the world frame, that is the inertial. So with respect to the base, there are different forces and torques that are acting on the vehicle from the suspension, tire, road surface, aerodynamics, and any external forces you want to give. Everything is acting with respect to this point CG, and that is what actually makes the vehicle move. So just go with the flow, you'll understand like why different connections are made in such a fashion. Next, coming to the suspension, there are there are many kinds of suspension that are available, like in terms of McPherson, double wishbone. In case of race formula vehicles, it is push rod suspension. And to easily switch between them, you have variant subsystems. You can, of course, make a small GUI based on masks, which makes you easy to switch between them. So how do you model these suspensions? So this is a schematic diagram that we have. So if you closely look, we have an upright, two wishbone pairs, so one is at the bottom, one is at the top. So near the lower wishbone, we have a push rod coming up, hinged at a point here that is connected to a shock absorber. This yellow and pink combination that you see is the steering rack, which will come in a minute. And the green one that you see is an anti-roll bar. Of course, this is one type of anti-roll bar. You might have something embedded within the chassis itself, but for simplicity, let's have this one as the anti-roll bar. So these are the bodies that you know. And now intuitively you know that each of them have certain degrees of freedom. For example, the wishbone can move in certain directions or can rotate in certain directions. So you need to use a ball joint. Typically ball joints are used. You can use even revolute joints. Simulation speed will vary because of, if you studied multipody dynamics theory, you know that some of the constraints you can remove basically, and the results will be pretty same. So if you can properly translate the 3D coordinates, you can use either a ball joint or a revolute joint. Bushing joints can be used. That means all 6 degrees of freedom can be used to additionally model the vibrations, but simulation time will increase. So it is called as judder because of variations in road surface, tire forces, and so on. You feel the vibrations which the driver feels in his seat, the driver feels through his steering. So all those can be modeled by using different degrees of freedom. All of those degrees of freedom blocks are available in SimScape driver. So that is about the wishbones. So these can rotate. You have a kingpin inclination, you have a caster angle. So these are set again by the hard points. This push rod again is hinged at this point, rotating about this point, and you have a damper or a shock absorber. Basically, it's a combination of spring and a damper. So here you have a prismatic or even maybe a cylindrical joint. So just from the schematic, we know that these are the bodies and these are the joints that we need to use to model the subsystem. Left and right, it is just symmetric. All the y coordinates, you make it minus y, and that's what makes it the right suspension. So let's see how it is going done. So I have a reference point. With respect to reference point, I'm going to all the wishbone points, that is the top upper wishbone and the lower wishbone points. I can choose the joints again with a variant subsystem, spherical joints, revolute joints, bushing joints to model judder, so on. I have the wishbone rods, the yellow rods that you have seen in the previous slide. They're connected to, again, either bushing the spherical joints, because on the upright, you need them to be connected. So that is what is carrier or the upright. Connected to the tie rod of the tire, or that is the steering. And connected is the push rod. So you have the push rod, you need to, because it has degrees of rotational, you have again spherical joints connected. There is a hinge in between, that is the rocker, and at the center of the rocker again it's a revolute, because rocker does not move in other directions, or it does not rotate in other directions. It rotates about only a fixed axis. So you have a revolute joint there. There are 2 arms for the rocker, upper and lower, so you have 2 of them. It's connected to the shock absorber again via spherical joint. Other end of the shock absorber is fixed to the chassis. So it is again fixed to the chassis. So that sums up how you build a very simple kind of push rod suspension. Shock absorber will come in a minute. So for left and right, simple. Don't have to model anything, just copy and paste the blocks. Everything is replicated. Just you need to switch from plus y to minus y to make left and right together. Now coming to shock absorber, we have seen previously that these joints have some compliance in terms of spring and damper. But what if the springs and dampers are not linear? What if they are non-linear? We cannot give those values in the dialog boxes for this. So we have something called as interfaces. So this is that interface. This is a translational joint I'm taking because the damper is expanding, so I have an interface. So I connect spring, damper, and a hot stop to tell that it is the limit of my damper, it cannot move. And you see force and position sensors. Basically, these are through and across variables that I'm measuring. So we, as in his previous presentation, has talked about through and across variables. So the sensors have corresponding meanings as well. So force is through the element and displacement is for the whole this thing. So that is an across. So I have position and velocity sensed together. These are inertial bodies to give you the inertia of the suspension. So that is covers the shock absorber. In terms of anti-roll bar, I have again the same reference point. From the reference point, basically you can rotate. So we have a revolute joint there. And now the anti-roll bar actually, and the load is increasing on left or right, and on the other side it is less. When you're cornering, there's a torsion that is developed in the bar. So torsion is about one axis, so that's why you have a revolute joint, and there's a compliance inbuilt. Here I consider it as a linear spring and damper, so I just gave inbuilt parameters. If you have more detailed one, you can use that even. Left and right arms that you have seen previously. So L joint, L body here and L body here for both left and right. It's connected to chassis again, or to the wheel basically, of this strut. So that is about the anti-roll bar. So the modeling principle for other kinds of suspension is the same, just that the bodies will vary and maybe degrees of freedom will be less, because if you take McPherson, we don't have an upper wishbone, so we have lesser kinds of bodies and lesser kind of joints. So, but the principles are the same. So, moving on to aerodynamics. So it basically depends on what kind of fidelity of the model that you are looking at. I have forces and moments in 3 directions, and for each of them I have lookup tables of the coefficients. If you want more detailed modeling, you have aerospace block set, which basically models all of these in more detail. But again, more details comes with a trade-off of more parameters. If you're able to get those parameters, you can use the aerospace toolbox to model all of them. But all the things that you have access to is the coefficients from the wind tunnel experiments. Using simple lookup tables and proper coordinates according to SAE norm, the equations are simple for drag, side force, and lift forces. So the convention is slightly different. So it again give proper directions to them. Similarly for the moments. And these are based upon angle of attack. So this is called 1 degree of freedom aerodynamics. So you have 2 degrees. You have 3 degrees and even more complicated models that are there. But this is the simplest one that you can come up with, and it actually pretty works well. So this block that you see is again from aerospace block set. So if you have an altitude and your pressure is varying with respect to altitude, so this block actually converts, absorbs all those things and give you the proper dynamic pressure that needs to go into the aerodynamics equation. So that is how simple aerodynamics can be. More details maybe you can find in the examples from aerospace block set. There is a flight model which actually gives you more details there. So you can refer to that. Next, moving on to powertrain. So the current model that we are going to see has following powertrain models. All of them, the principles are the same, but the additional components is what gives them more fidelity. And maybe to how do you design or characterize your full vehicle, whether you want a front wheel drive or a rear wheel drive or all wheel drive in terms of 2 differentials, or individual motors called hub motors if you want to use such kind of thing, and battery with heating. Motors and battery with heating and with a cooling circuit for the overall. That is 2 motors with plus battery, all of them thermal components along with cooling. So basic structure still remains the same, like what Weir has shown in his presentation previously. So I have a linear relationship for now. Let's assume throttle is linearly connected to the motor control. So I have the motors inbuilt, the battery, each of them connected to differentials. So a torsion differential is slightly more detailed because you have sun gears and worms in between. Normal differential is also good, but torsion differential actually prevents slip in kinds of certain ways, so it's somewhat advantageous. So that's why I put a torsion differential here. Need to build them. It is not a custom block. Differential is available as is, but other basic blocks are available for it also. And what you see here is a battery with, I'm measuring the charge. You can also measure the SOC, measuring the voltage that is dropped because of consuming power from the motors, connected to DC-DC converter, 2 motors, and I'm connecting to something called a Simscape bus. So many of you might be familiar with Simulink buses. So there is something called Simscape bus as well. You can feed the physical signals. Simulink signals will not go through. Simscape signals only will go through. And their domains are conserved. So if you input a mechanical domain in, you will get the same mechanical domain output. You can mix and match basically. Need not be always mechanical input. You can give an electrical domain into the same bus, and the output you can pick up all of them as is. So these I'm using so that I can use them in variant blocks that I've shown previously, variant subsystems, and you can choose which is actually suiting you best. So it helps in making your decisions better. So with the cooling system, same thing, but now the motor has a thermal mass and it is dissipating heat via conduction, convection, and there's a cooling tank around it. Rest all, everything is the same. Same thing for battery. You again have a thermal block for the battery also. Thermal ports are available for battery. Again, it requires more extensive parameterization. Some of them you can find from the data sheets, but others you might have to do some kind of experimentation to validate your data. So those are quick overview of these subsystems. So next two, I'm going to take a certain more details. So why I'm going to take tires in more details is because it's not just on a subsystem level, it affects the whole range of performances. So for example, on the right side that you see, what are all the things that the tires affect? It affects the mechanical behavior, the acoustics, that is the noise and the comfort levels that you feel, steering and handling comforts, stability, aquaplaning, that is when you're driving on wet roads or basically on icy roads and so on. So that is what is this, aquaplaning, wet and winters. If tire is worn out, your vehicle behaves completely different. Or if you have all 4 tires of 4 brands, if you're using on a vehicle, God be with you, something might happen because generally it is not compatible in terms of handling. It's not unsafe. It is unsafe for neophyte drivers. Expert drivers might be able to manage with such kind of situations. Then noise and fuel consumption. Fuel consumption is a very huge topic, especially with electric vehicles coming in. It's a big trade-off. If you put lower rolling resistance, that is a dissipative force from the tires, it's a tough choice because yeah, your battery might be conserved, but you won't have the grip on the road. Your brakes, even if you brake hard, the vehicle skids, but you won't come to stop easily. On the other hand, if you increase the grip, rolling resistance increases and your battery life will go down. So it's a very careful trade-off. So basically, the tire affects the entire spectrum. Correspondingly, there are many tire models that exist. So the simplest one is Magic Formula or the Pajeka tire model. A bit higher is the Swift model. TMEZ is again by Michelin. It is a proprietary tire model by them. It's also available commercially. Of course, a very detailed model is available from F-Tire. These are called physical tire models. MF and MF Swift are semi-physical or semi-empirical tire models because it's basically curve fitting with some physics added on top of it. F-Tire is some physical tire model. Of course, the king of all these things is FEA tire models. It takes like days to simulate just a very small segment of tire behavior, but that is the strength of it in terms of computational power and in terms of fidelity as well. But to run in our simulations, we cannot wait such long, so we have other tire models for our thing. And their frequency levels, and depending on this, you need to choose a tire model for your simulations. Most often, MF Swift is a good bargain in between. Don't have to be expensive, don't have to be too loose, but it covers most of the spectrums. So what is this magic formula? Magic formula is basically developed in 1980s by Professor Pajeka from Delft University. All the forces and moments are similar in terms of their equations. That is why it is called as magic. And all of them have similar inputs. So load, slip ratio, longitudinal bias, slip angle in the cornering side, camber, turn slip, and longitudinal velocity. This is a general form of equation. You have, of course, the sister components coming in between, depending on camber, inflation pressure, loads, so on. So the equations run into pages. And these parameters, each of them are shown graphically. So the T is the peak value, and this is the stiffness, that is the K and B. C and E are basically depend on the non-linearities of the tire model. So this is the graph that, or the flow chart that we have seen previously. We estimate them from the experiments and then finally use it in the simulation. But how do we estimate? So on the top is the skid roller that you see, that is currently available with JK tires, which can run all the vehicle level tests. On the bottom, what you see is a Simscape multi-body digital twin of the same virtual skid roller. So it is capable of doing all the tests that it will do, and it will give you, on the top, you can see the graphs that are being generated. So it is basically doing the cornering test, and we will be able to identify lateral forces versus aligning torque with respect to slip angle at different camber angles. So that is the animation that you see here. So it is cornering test with camber. Not only that, it can do pure slips. This is a pure slip that we have done here. It can do combined slips, wet and dry camber, launch transients. I'll show what is transients mean and why they are important.
Krishna, sorry to interrupt. So which tire model are you using over here in this one, in this model?
Yeah, it is MF Shift model.
Okay.
And the good thing is with 2021B, you already have a Simscape multi-body tire model already available, so don't have to look anywhere else outside. But it is there to pick up you right from the simulation slide.
Yeah.
So these are the transients that I mentioned. So many of you know, for a transfer function, if you give a step input and the response is not immediate, it has dynamics in between. So on the left, what you see is longitudinal, that is step braking if you give step braking pressures. The slip does not change as is. The yellow one is the transient, and the pink one that you see, or the magenta color you see, is the steady state responses. In reality, what we see is the yellow one. On the top, you see is the braking force as measured on the tire. So again, we have some issues. So from here, you can very well understand that when you run on an ABS, especially on racing tracks, ABS should be working well because your tire slips out. So because of that, these transients play an important role. You need to measure them and account for them in your tire parameters. Similarly, on the right side, if you see, you have cornering transients, and with different speeds, you have different behavior or the dead bands within the lateral force and the aligning moments. So these dead bands, first of all, affect the vehicle behavior. Second, affects the driving feel of the driver. So the driver might feel tensed because he goes in a turn while returning back. If he does not feel the torque, he does not feel confident about the road holding capacity of the vehicle. So the driver gets anxious. So these things need to be measured, or at least some theoretical values need to be put up in your tire models. These are, of course, more detailed in terms of Swift modeling, where see for very low speeds how the forces in X and Z directions vary. You also have combined slips as well, where the cleats are cross, and you can measure all kinds of ride parameters. So it gives you the comfort. Typically, we say for passenger cars, the ride frequency is about 1 hertz. So those come from this. It's not just the suspension, even the tire. The tire is rigid, frequency shifts. If the tire is too loose, you feel what you call a lagginess or sogginess in your ride gear. If it is stiff, you feel its ride is very rough. So it's a very careful trade-off that you need to choose. And it depends on what kind of tires that you're using. Low aspect ratio tires give very good handling performance. On the other hand, ride performance decreases a bit if the road is wavy. On the other hand, higher aspect ratio tires gives good suspension kind of thing because you have more rubber in it, but handling will be a bit poor because the transient dynamics will be too slow for you to respond. So there are so many trade-offs that exist with respect to tires. But good thing is in mathematical models, you're able to capture all of them. So this is one such machine which we use to capture the frequencies that we have seen previously. That is for the ride test and so on. So this is the wheel we mount, and we have cleat placed here, and this drum rotates. We measure the forces across the hub of the wheel. So finally, if you mount different wheels on different things, again, the right side what you see is in MATLAB Simscape multi-body that simulation is running, and left side what you see is the power spectral density measured at the tire hub. So it gives you feel of how good is your tire holding the road and how the driver is feeling comfortable on the tire riding on a specific tire. And to give you a flavor of data, experiment gives you this kind of data, that is the raw data. You need to have some kind of understanding of your test equipments to understand and filter it, not to induce additional lags or additional dynamics in your filtering. You need to be very careful. On the right side, what you see is the fit performances. Again, lateral force and aligning torques and so on. So this way we can actually validate all the tire models, measurements, tire parameters, so on. So, but how do you get all these parameters to get your simulation started? It looks like there are hundreds of parameters. It runs basically into hundreds. Where do you get all of these parameters to kickstart? So from 2021B, that's the next slide. From 2021B, there is an SUV tire that comes as an example. So all the parameters are suiting for an SUV tire, SUV vehicle basically, and you can off the shelf use the tire file as is. So enough of that. Now coming back to a simulation model, this is again the Simulink mask, Simulink block mask that I use to model different tire models. Siemens tire is the commercial version of Magic Formula tire that is currently available. You might be available even for an academic pricing for that. MF eval is available on MathWorks File Exchange. It models many of the dynamics to a very good extent. It's done by Marco Furlan. It is converted into Simscape now. It is also available. So you can use the model as is. But if you're using the latest version of MATLAB, that is 2021B, neither of these you can directly use the toolbox multi-body tire, Magic Formula tire. And these are some other additional settings that I'm choosing to. So these are tire log that I'm using by default. So which comes with the toolbox. Some more additional settings like what kind of dynamics you want to choose, how many slips you want to select, you want to decouple them or couple them together, so on. So these tires are we have seen previously there's a powertrain that is coming in with Simscape bus, so that is connected here. Similarly, there is again a bus coming from brakes. Both of them are connected together here. So that is what is the green color lines you see, that Simscape bus coming. The gray color lines are the physical locations in terms of Simscape multi-body connections. So that is what is in the gray lines. And they need to be positioned and aligned in certain directions. So that is why you use these rigid transform blocks to align them properly. And you have a revolute joint because the tire should rotate about an axis. So the joints have certain friction and damping. The viscous losses are there. So we model them. You can use a full primitive gimbal joint when you are going low on suspension. So we have seen a very detailed suspension which basically accounts for all the caster, camber, all other profiles. So we do not require them here. But if you just model them as a spring and damper and you want all the camber caster profiles to be proper, you can give them as lookup tables to corresponding revolute joints here. So X corresponds to camber because it's moving in X direction. Y corresponds to toe profiles, steering angle, and so on. If you do not have a multi-body model for steering, caster, and other stuff. But here, since we have all of those things, these are commented and only Z revolute is required. Of course, you have CAD models specific to that. If those are for basic electrification, this does not have any, because all other things are accounted for within these blocks. So this is what I'm telling. So with 2021B, you have this block coming up, which you can use as of off the shelf. With again the parameters there, you can look up this example for the tire file. So again, the parameters are validated for an SUV tire, and you can just take it off the shelf and use it for your simulations. So that is on the tire side. So let's go into the steering now. So steering from the front end looks very simple. You give a rotational angle on your steering wheel and the tires move certain direction. But they have very important task of giving you the feel of the road, the feel of the entire vehicle, dynamics that are going on onto your hands. So there are many cues that the driver feels. So one is the visual, one is the audio cues, and the other is the haptic cue that comes from the steering from here. So that needs to be captured by the whole system that is running. So in this case, we are modeling a column EPS, electronic power steering, with column assist. So we'll see how are we doing that. Rack has its own dynamics. Of course, suspension effects, because there are profiles, camber caster profiles, which actually changes tire behavior, which in turn propagates the forces and moments through the rack, through the steering columns. So that is how the steering plays a very great important in feeling the road. But to model them, there is no friction block that is out of the box available. There is a friction block in rotational library, but steering friction is slightly different. There is a lot of literature around that you can easily find out from proper journals like Elsevier and so on, why the steering reflects in a different way, the friction element. So this is the friction element. To model them, you have custom Simscape language. There's a Simscape language, and you can write on all the equations. It's very simple. Once you write a small equation for that, other things is just integration with other blocks. So you don't have to write the full equations as described in various theses, various textbooks, and various research papers that are available online. So that is a very big advantage using Simscape. Just make the component itself customized, but the whole system is now again block by block connection. Just wire up them together, and we have the systems built for you by the Simscape at the back end. So what you see on the left side is the custom code, that is the SSC file. It's a .ssc file, that is the Simscape custom component file. And this again is the Simscape or the Simulink mask of the entire steering model. So I have the mechanical module with upper column, lower column, that is the torsion bar, the rack and pinion with inertia, stiffness, damping, friction, all of them. And again a power assist. So how do we model power assist? That we come in next coming slides. And its physical locations in terms of hard point. So you need to say that it is this so and so distance from the wheel, so and so distance from the axles, and so on. So this front suspension will accommodate all of them. The model is also very closely validated with IPG car maker that is having a professional steering model. So the model matches very closely. You can see because the diagrams are same, but parameters, the graphs that you see, all of them do match. So column assist, it is basically dependent on how much torque you sense at the torsion bar, and a current is supplied to a motor that is present in the upper column, connected by a warm gear to this column, and that is what gives an additional torque, which again propagates through all the way and steers your vehicle. So the graph between torsion bar torque and the current is available via lookup tables. You can do it a lot of math stuff on it, but easiest way is to have a lookup table. I have a lookup table now. Use a PID controller because I give a current here, the DC motor with some dynamics of motor shaft, other things there, controlled by a warm gear, and I measure the torque, compare it with what is coming from the lookup table or not, and just the current going to the motor. So that's how the loop works. And I give it to the bottom here. So that's how the power works. Now let's jump one step ahead, one step back, and see what is the friction that is doing here. So the bottom thing that you see is the friction that level off the shelf from the library. And the top one that you see is a custom block that is model. And the corresponding graphs are here with respect to a frequency sweep of inputs. The left one is the library block off the shelf. Right one is the custom block. So the first thing that you see is there is no gradient friction, but it has a very smooth gradient because every small torque that is generated by the road and the tire interface is felt by the steering. So the friction does not ramp up, that has gradient, and it has small changes with respect to frequencies. So those need to be accounted, but in the others, it's just a plain same thing. So this is a cross plot. In the time domain, you see the pink one is with the custom block, and the blue dotted is this. Top yellow is the input of the spectrum. So the variations, and these are captured with the custom spring blocks. All of them can be written by a custom Simscape language. So that steering model is what has generated the figures that we have seen previously. The 4 cross plots moving on a sinusoidal test, that is what giving you the driver feel. Now moving on to the brakes. Simscape has very detailed examples of extensive brake modeling. For example, you have vacuum booster and a tandem master cylinder. You also have fixed caliper brakes, extensive models to them. Of course, it requires a lot of parameters. You have access to them, well and good.
Krishna, hello?
Yeah.
We are losing your voice actually.
Hello?
It's like, I think, yeah, hello.
Yeah, sorry,
okay. No. We were losing your voice actually. As in, there was some network issue from your end, I think. But
okay. Fine. Okay. So should I go back and come forward, or should I continue?
No, continue. There's no problem. I mean, there's continue. In case like if it again happens, then you can just I think just to save the bandwidth, you can close the video.
Oh, okay, fine. Okay. So if you don't have these 10 level blocks, and this is what in our case. So in this, I have 4 disc brakes combined with an ABS model. So the ABS module has of course, when the ABS is not activated, how the pressure should vary in terms of Simulink equations, and the ABS kicks in once certain conditions are crossed. For example, the tire is slipping or going out of control, so ABS kicks in. Most of your values, this is the tire curve, force versus slip curve that you see. The bottom one is for the braking, top one is for traction. Here is traction controller TCS, and here is the ABS. ABS needs to operate in this region because if you go here, you'll fail. The vehicle will go unstable. And these are from one of my publication where use a Bosch ABS. How the algorithm is there, that is what is shown here. This is the Bosch flow chart. You can also use sliding mode control. Some of you in the non-linear or advanced control systems might be knowing what is the sliding mode control. So all the equations are there in the paper. You can find from there how these are implemented. So this is the paper. And the important thing is both the tire and the ABS algorithm, I mean, have a very important role on how the overall ABS performance is varied. So that is what is the bottom plot shows here. I have few tire parameters that are varying, and the sensitivity of the stopping distance of the braking algorithm for both the ABS algorithms is what is shown here. From the previous graph, you might see that, okay, sliding mode is very smooth, but you see it is varying across parameters, so it is not robust. On the other hand, Bosch you might see is fluctuating a lot, but it is robust. So just from one graph, we cannot determine. And the paper has extensive coverage of how the simulations are done. It's a humongous number of simulations, more than 2 lakh of simulations with a combination of tires that are performed. And you get a point cloud. This is basically a 5-dimensional because these are 4 and fifth one is the stopping distance, all the 4 tire parameters. These are compressed using mathematical equations into a 2D graph. And this 2D graph is further analyzed to get this graph. So it's a huge work that is done. And that is why you need to be very careful with your tire parameters once you design ABS. If you change any of few parameters, it might lead to a different behavior altogether. You might wonder your algorithm is very good, but why the performance is not good? It might relate to not using proper tire parameters. So coming to the driver, depends on what kind of situation you are and the driver changes. Either you want to use an open loop or you want to use a closed loop. Closed loop, the path is already known and you need to give the inputs accordingly. In open loop, you know only the inputs. You don't have to follow a path. You just need to give a standardized input, for example, a test protocols that, for example, in the previous slides we have seen the sign test and how the graphs are generated for the cross plots between steering angle and lateral acceleration, yaw rate, and so on. So that is where you use an open loop driver. Vehicle dynamics block set has longitudinal driver, lateral driver, and the robotics control toolbox has pure pursuit. There's a video made by again here. There's pure pursuit, so you can watch the video to make this one. But how do you decide upon which points to follow the path? You know X and Y coordinates, but how does it go? So there is this MATLAB Excel Innovation Projects where Jacob has basically submitted his thing and he has won the competition. So this is what currently I've used. Previously I used different lookup tables and other control systems to modulate the speed according to the lateral acceleration. Because in the tires we have seen the combined slips have an effect. So when you brake and corner together, the tire loses its control very easily. So taking all those into consideration, we need to have the slips and the speeds at different points with respect to the distance covered. But here he has used a point mass simulation. Of course, it is not accurate when you put the full tire model into that. You need to again add some more of your control systems to tune them according to the tire slippage, the lateral acceleration behaviors. But this is a good starting point for you to develop other control systems around the existing point mass model. If you use the point mass model, the graph generated from here will not match with the full vehicle model because here it is an idealistic one, but here you have a realistic models. That is why. So I think we are right on time. So that is a quick overview of the modeling. So what are the key takeaways from the whole presentation? So first is if you use variant subsystems, you can easily swap across them. You have block masks where you can easily switch between parameters or different variant subsystems or even change the behavior of how it is running. For example, in the tire models you have seen by giving different changes, you are changing different parameters or different behaviors in terms of slips, dynamics of the tires and so on. Simscape and Simscape multi-body interface. So the degrees of freedom you have, for example, revolute joints or gimbal joints or prismatic joints in terms of translation and so on. But how do you interface to a complete Simscape network? For example, steering that I have shown is a complete Simscape network. It is connected to wheel that is a revolute joint and a rack that is a prismatic joint. So the connection is using these two interfaces. Then you might say that some of the components are missing in the library. How do I model them? I have built the entire system on Simscape, but Simscape does not have some of them. Simscape language is very simple. The equations are the same. how do you write it in normal MATLAB scripting or Simulink blocks. the same thing, but you have additional units. They are having power equations in between. Through and across variables need to be properly taken care of. Once you are taking care of those things, the equations are pretty much simple and clear. You have all the dynamics that can be accounted for. So you can even model forward and inverse dynamics with the Simscape blocks. What I mean forward is, in the electronic power steering case, what you have seen is I give the forward torque in terms of current. So that is, I'm giving the force, that is the cause, and I'm sensing the effect, that is the rotation of the mechanical components. In the other case, in the steering, I'm giving the steering wheel angle, because that is what I can calculate. And I want to sense the torque, that is the cause. The effect is the steering angle, obviously, because when we drive, we give only the angle. We do not worry about the torque that we give. So I give the angle here, and the components have the capability to give out the torque as well, the corresponding torque. So that is possible with for each and every degree of freedom in Simscape. So that is a very big advantage in terms of both forward and inverse dynamics. Finally, data and parameters are the currency for all the simulation that you have seen till now. Any slight mismatch in parameter, for example, in this case, you might target for a certain lateral acceleration. Your system is very good. I mean, the model is modeled very nicely, the simulation model. Everything is perfectly fine, but you never reach the 4 meter per second square. You're stuck at 2.5 or 3. It is because some parameters are not proper. In this case, for an SUV, I'm using an hatchback tire. So you can never expect the performances will match. Even other side is on a hatchback, if you put an SUV, you will feel a lot of inertia, and the problem is you'll have very too slow of transients, because you cannot produce such kind of torques with a small hatchback. So that is a very simple use case with respect to tires that is valid for all other subsystems as well. So putting all the pieces together, on the left we have an SUV which is fully validated with all the experimentation that we have seen previously. That is the steering robot, RT3000, and LVDT sensors for suspension, KNC measurements, and so on. All of them are validated on this SUV, and that is why you'll see it kind of magic. On the right side, it is basically guesswork of many parameters. The tire is, the CAD is what you see is for a race, but the tire is for an hatchback tire. So performances will not match. Let's run the simulation and you will be able to see the difference. Let's go with the SUV first. I'm doing a double lane change, open loop. So the driver does not control the speed while the maneuver is going. Does pretty good job on the left side, because it's an SUV and I'm putting an SUV tire. The same tire that you get with the latest release of MATLAB. Right side, I'm using a 13-inch or a hatchback tire, that is a smaller tire, because it should match the height of the tire. So let's say I'm using a smaller tire, but its characteristics are completely different. So it accelerates, but nothing much is going to happen. It will go out of the path. So many cones are hit in this case. If you reduce the speed, yeah, it does a good job. And finally, if you want the same things modeled together, if you want to run it on a full racetrack, so this is sped up. This is how it runs on the full racetrack. So the pitching that you see is because of ABS, and you are decelerating at a very high rates. So there's a lot of pitching that is happening. And the speeds, you can see it is quite this time. So once it is done, it will have the velocity profile and the tracking as well. So this is the road with its road width, and the color shows you the velocity profile that is here. And actually, the points on the graph shows how it is being tracked. At corners, you see that it is going off the track, which is obvious because brake and also corner at the same time, you lose some of the friction because the friction ellipse has to be obeyed. The total force is the same. It just redistributes among the longitudinal and cornering forces. So that is why there's a problem there and car goes off out of the track. And again, it comes back because the driver adjusts to it. And yeah, that is from my side. Maybe we can have 5 minutes of Q&A if have any some queries.
Yeah, Krishna. So what I'll do is, just interest of time, I'll just share some resources and then we'll take the questions in that case. Okay.
Yes.
So let me quickly, I mean, I think we crossed time, but still, I think thanks for being patient. And let me share my screen. Yeah. This is one of the video tutorial model and simulate automotive system using Powertrain blockset. So it introduces you to what is Powertrain blockset, how Powertrain blockset can be used, and how Powertrain blockset and SimScape can be interfaced. So we'll share this link as well in the chat box. Have a look into this. And with this, we'll quickly just go around certain resources which we also shared in the last session. So this is one of the student tutorials and videos where you will find relevant different competition videos related to automotive, aerospace, and robotics as well. And further, we spoke about this winner circle last time also, that if you're winning team and you have used the tools, let us know. We would definitely love to feature you on our MathWorks webpage. And coming to the Facebook group, which we were talking about, and where we'll also releasing the links of all these recorded webinars. And yeah, again, answering to the question of are we going to share the presentation and are we going to share the videos? Yes, we are going to do that. We'll send you via email, and also on the Facebook page as well. We'll share. We'll share on the MATLAB Sim Racing launch. Yeah, and we'll spoke about all this. And just the final thing, what we wanted to share is that this is our contact, racinglaunch@mathworks.com. If you have specific questions or if you are looking for specific models, just write to us at racinglaunch@mathworks.com and we'll share you the resources. And then we have the last session, which will be given by my colleague Sam on communicating with CAN networks. If you haven't register for this one as well, and you learn how the simulation model what you have created, you can communicate with the CAN networks. And one thing which would definitely love to have is that if you can fill out this survey. Meanwhile, when we're taking the Q&A session, this is the link that would definitely help us to build content and also answer certain your questions, and it will let us know that where we should focus on helping the student teams.